melting points and boiling points. So if I remember correctly, the video ended on this slide, but it didn't provide any answers. The difficulties on this is the most difficult one. I don't know why I decided to do the most difficult one at the top, and then the least difficult is down below. I'll do a full walkthrough on the least difficult and leave you to go through and consider what's going on with the kind of intermediate difficulty ones. And then the most difficult I'll also do a full walkthrough on. All right, so let's go through and address how we could look at 4. How do we decide which one has the higher melting point? Okay, so if we're looking at higher melting points, what are we concerned about? Well, we're talking about how we transition from a solid, yes, to a liquid. Well, what prevents that transition? The prevention of that is your intermolecular force, or your IMF. If I have a higher melting point, I have to put more energy in to break that force, which means higher means stronger intermolecular force. So when I'm going through to predict which one has the higher melting point, what I'm trying to do is identify the intermolecular force that is highest in strength. So we have ionic, hydrogen bonding, dipole-dipole, and London dispersion forcing. Okay? But remember, we don't see those inherently. What we would have to be able to do is to interpret them from the bonds shown in our individual structures down below. So if we go through and evaluate, we would have to be able to convert our ionic into a bond type. That would be ionic. Our hydrogen bonding was polar covalent. Our dipole-dipole was polar covalent, and our London dispersion was non-polar covalent. This is why we started with that slide of trying to come up with all of those comparisons so that we could evaluate these things. So, next phase is how do we go through and interpret some of that? You are responsible for being able to take this formula and turn it into a Lewis structure. Okay? And we talked about this when we talked about Lewis structure. The basic patterns on the connectivity on how we align these things. Our formula is written in a way to help guide us to that Lewis structure. The same deal applies for the other one, and we should be able to jump to that. Do we need the Lewis structure? Well, we'll talk about that in a second. Okay, so let's go through and look at all of the bonds present in our purple structure. Okay, all of these blue bonds that I'm showing have an interesting characteristic. They are all carbon to carbon or carbon to hydrogen bonds, which means those blue bonds are all non-polar covalent. If they are non-polar covalent, they lead to London dispersion forces, which are weak, which would mean a low melting point. Okay, so that's not what we're looking for. As we continue through to look at our molecule, we may note that we have the oxygen bond in there as well. Those orange bonds, carbon to oxygen and oxygen to hydrogen, those are dipole-dipole bonds. The polar covalent bonds. The polar covalent bond leads to a dipole-dipole force. If I have a dipole-dipole force, I should now consider, do I have hydrogen bonding? And sure enough, I do have a hydrogen connected out there, so I do have hydrogen bonding as well in this molecule. So if I look at all of the forces, I have London dispersion, dipole-dipole, and hydrogen bonding. When looking at melting points, officially it's the strength of all of the forces, okay, which will become relevant when we look at 1. But at a first approximation, we can just go through and evaluate based off of the strongest force. So which one of these is the strongest force? Well, hydrogen bonding. When I went through and did that analysis, I did it based off of the structure drawing. Did we have to go to the structure? Could we have done it from the formula? Okay, well, let's look at the formula. What is bonded to that carbon, most likely? Well, there's a hydrogen right next to it. Yep, which means that's probably a non-polar covalent bond, which then means London dispersion forces. Okay, if we go through and continue, we might see, and then this is where it's going to become a little bit tricky. We have this oxygen, and then we have a red hydrogen, and I'm going to call it a purple hydrogen. The red hydrogen is the only one connected to the oxygen. Okay? That generates a polar covalent bond, which is now a dipole-dipole, which could lead to hydrogen bonding because we have the hydrogen bonded to oxygen. Okay? The purple hydrogen is officially bonded to, as we see up here, the carbons. Okay? Not to the oxygen. So it's not generating a hydrogen bonding force. Okay? That will become relevant when you go through and look at, I believe, actually 2 and 3 both have a system where there are some hydrogens next to oxygen that aren't bonded to oxygen. Looking at the structure helps you see that. Looking at the formula becomes a bit dodgy to evaluate, so make sure you at least understand the notational differences here. We should then go through and do the same argument with our other compound, compound B. When we go through and look at compound B, we're going to end up with our London dispersion forces again. One of the things that's nice is we could immediately ignore those because they were the same in both compounds. As we continue across, we do still have a polar covalent bond in orange, which would be a dipole-dipole force. We don't have hydrogen bonding, so maybe A is going to be the stronger one. What do we have, though? That purple bond is a metal and a non-metal. We have an ionic bond, which leads to an ionic or electrostatic force. The ionic electrostatic force is the strongest force on my list. Based off of the rules that I just went through and elucidated out here, I want the strongest force for my compound to have the highest melting point, which means my answer is 4B. Okay? All of that was kind of thought process on going through and doing this. And you may think that, God, that's a lot of work. Most of that work can be internalized if you do practice. If you don't do the practice, then you won't be able to do any of the work, and all you'll be doing is guessing. You're getting a 50-50 odds here. Okay? So please spend the time to do the work, identify the bonds, identify those forces, come up with those ranking systems, and it will help out. Okay? The last one that I said that I would walk through, which I might have to erase some stuff for, unfortunately, because that one's kind of long, would be looking at something like this. Okay? For A. So we're going to erase everything else off of this, or most of it off, and try and evaluate this. Okay? In our simple fashion, what we could go through and do is just look at our formulas. That's what I said we could go through and do. We don't have to look at the full-on structures. Okay? If we look at 1A, we have carbon to hydrogen, carbon to hydrogen, carbon to hydrogen. All the atoms in that structure are carbon to hydrogen, which then means we're looking at non-polar covalent bonds. Non-polar covalent bonds lead to London dispersion forces. That's the only force that I see possible for this compound, which would suggest that it's not our answer. Okay? When we go through and look at B, we see a similar issue, though. All of those are carbons to hydrogens. So it's still a non-polar covalent structure, which still means London dispersion forces. Okay? So is this then a trick question? Which one has the higher melting point? They have the same melting point? No. Okay? And the reason being is that if you were to say, I don't know, this is my version of a little baby. So there's a little baby crawling on the ground. Looks like a dog. Oh, well. Okay? So there's our little baby versus, let's pretend this looks like the Hulk. Okay? And you had to go through and then fight this one of these two people. There you go. 6-pack, big legs. Okay? And we were going to go through and look at a fight. Well, you would probably say you would rather fight the baby because you could beat the baby, but you aren't going to beat the Hulk. Okay? But what happens if we now change this argument? Instead of now fighting baby versus the Hulk, let's see, can I pull this off? Copy. You're fighting one baby, or you are fighting... Oh, wow. That copy did not work the way I wanted it to. Or you are now fighting still babies, but now instead of just one of them, you have to fight 1,000 of them. Okay? Are you still going to choose how is that going to change things? Okay? And let's ignore the fact that you have to deal with the burden of having dealt with this many babies, however way you want to look at it. Okay? Just battle to death, that's just the way it works. You're probably going to favor one over the two. So the number of intermolecular forces contributing also changes your melting point. When we look at that larger molecule, okay, what happens? Yes, at each individual point of interaction, we generate a London dispersion force. Okay, and that individual London dispersion force is the same strength. But when we look at A, we'll get, say, 4 interactions. When we look at B, we're going to get a whole lot more interactions, which means the sum total of those forces are going to contribute to our melting point, and B ends up being the higher melting point because there's more of those weaker forces present. Okay? So when we're thinking about melting and boiling point, realize that at a first approximation, it's just the raw strength of the intermolecular force that dictates. After that, there are other considerations that need to come in. The size of the molecule, how big it is, how small it is, how folded up the molecule is versus how stretched out it is. There's lots of other things that contribute to melting point and boiling point. The simplest attempt with melting point and boiling point is the strength of the intermolecular force, which means when you now go through and answer 2 and 3, you should be selecting the molecule in each of those pairs that has the strongest intermolecular forces. I'm just going to say you're going to have to ask me what the answer is for those in our conversations through WebEx or in class if this is a much later semester. Okay. Continuing on, phase transitions. I do just want you to be aware of this. Okay, so here's a diagram to kind of represent this pictorially. We want to get an idea of our heat versus our temperature. So I'm going to take a block of ice at a very cold temperature. Okay, so that block of ice I'm going to say is negative 100 degrees Celsius. Okay, and now what I'm going to start to do is add heat to it. Okay, when I add heat to it, what's going to happen to the temperature? Well, the temperature should start to rise as I add that heat in. Okay, as I continue to heat, though, eventually I'm going to hit the temperature of 0 degrees Celsius. Now what happens when I add heat? What's going to happen to the temperature? Okay, for those people saying, well, it's just going to continue to rise. Okay, does it though? Okay, if I take a block of ice and I slowly heat it up to 0 degrees Celsius, and then I continue to add heat, does the ice all of a sudden go up to 5 degrees Celsius? Okay, or slowly go up to 5 degrees Celsius? It's progressing upwards, or does it stay at 0 degrees? Okay, and that becomes kind of a challenging thing to observe on the solid side of it, on our ice side of it, and it'll be a little bit more sense on our gas side. As we add heat, the temperature actually is not going to change. It's going to flatline at 0 degrees Celsius. Okay? But eventually what happens? All of that solid ice becomes a liquid. Okay? Once it transitions to be a liquid, as I continue to add heat, the temperature is going to rise again. Okay? Eventually, again, it's going to hit a spot where it stops rising. Okay? At 100 degrees Celsius, I've now added enough heat that the temperature gets up to 100 degrees Celsius, and again, it flatlines. So this is where I said it makes a little bit more sense. Think about when you boil water. Okay? You boil water, it gets to 100 degrees Celsius. Does that mean all of the water instantly became a gas? No, you're still adding heat, and it's still boiling, but the temperature doesn't change. The temperature is only changing when you're just a single phase. So what's happening in each of those kind of flatline areas? Well, those flatline areas are our phase change. It takes energy to change phases, to go from, in the red phase, liquid to gas, and the blue one from a solid to a liquid. Okay? As soon as we convert all of the liquid across to a gas, well, then again, our temperature climbs. Okay? So you may have heard references to caution, steam in these lines, caution hot, freak out about it. People are like, well, it's only 100 degrees Celsius. How bad can it be? No, it's not 100 degrees Celsius. If you see a steam line, it's probably not at 100 degrees. It could easily be clearing 200 degrees Celsius. We're looking at a gas that could theoretically be infinitely heated. So it could be infinitely hot. Liquid caps at 100 degrees Celsius. Solid ice caps at 0 degrees Celsius. You can get really, really, really frostbitten, right, by touching ice that's at the bottom of the Antarctic. Why? Because it's probably a lot colder than 0 degrees Celsius. And so brief contacts with that could result in instant cellular death. The same thing is happening with our gas at the high end. We could go to not infinitely low temperature, we could go to 0 degrees Kelvin, and then we have an infinite max on our heat. Okay, let's ignore the phase change to plasmas. Okay, so what I want you to be aware of is these phase transitions. You are still constantly adding energy in. Where this becomes kind of interesting is, say, if you move into 151 and we want to know how much heat was put in, there's going to be a heat associated with that phase change. There'll be a heat associated with this phase change. There'll be a heat associated with the change in temperature. Okay, so if I want to know the total amounts of heat being transferred, because remember, I can't directly observe heat, I can only measure temperature. If I want to figure out what that heat is, I would have to kind of monitor the temperature and make these kind of correlations back using a diagram like this. Okay, and that's kind of neat. Okay, that's really all I want you to be able to think about and recognize, is that there is heat involved in a phase transition that does not change the temperature. A big new section in 151, for those of you that go there, is a section on thermodynamics, which is all about heat transfers. Okay, and that becomes a big deal. Okay. Vapor pressure, another application of our intermolecular forces. This is kind of a fun question for me personally. I like this. Okay, so let's go through and walk through high vapor pressure. What does it mean to have a high vapor pressure? That means there's lots of gas. Well, if we have lots of gas, and this is lots of gas above a liquid, right? If I have lots of gas above a liquid, what does that mean about the intermolecular force? Well, then that must mean that the intermolecular force is very weak. Okay, why does it need to be weak? Well, that's why it's transitioning to the gas phase. Okay, it doesn't need a lot of energy, and so it's jumping from the liquid to the gas right away. If I have a weak intermolecular force, that means I would be looking at a strong bond. Okay, our weak intermolecular force would be, say, London dispersion force. A strong bond would then be a nonpolar covalent bond. Okay, so I have to be able to reason through each of these steps. So now that I have these kind of steps in play, I can now go back and look at my answer choices. If I look at answer choice E, that is all nonpolar covalent. Nonpolar covalent. Whoops, S is now fitting in our everything else category. S to C isn't in one of those places. Since it's not a metal, it's not ionic. And since it's not carbon to hydrogen or same to same, that must mean that that's a polar covalent bond. That polar covalent bond is going to lead to a dipole-dipole force. That dipole-dipole force, if we had our kind of chart memorized on our strength of our interactions, is kind of a middling intermolecular force. Okay, it's definitely not the weakest, okay, but it's still pretty on the low end. So we would continue that analysis through all of these. D, C's, and nonpolar covalent, nonpolar covalent, nonpolar covalent, chlorine. Chlorine's a dodgy one because it looks, depending on who you talk to, like uranium if I wrote it, or it looks like carbon as part of the carbon backbone. Okay, that chlorine is now a carbon to chlorine, which fits in our polar covalent, which means dipole-dipole. This should already set up alarm bells in our head saying both D and E are wrong because they have the same strength force. As we continue through C, nonpolar covalent, nonpolar covalent, nonpolar covalent, that oxygen to C is again going to fit our polar covalent category, which means dipole-dipole. Okay, again, that fits in our category of the others, so all three of those are the same. It's going to be hard to differentiate those. B, nonpolar covalent, nonpolar covalent, nonpolar covalent, nonpolar covalent, nonpolar covalent. These bond in that compound are very strong bonds leading to very weak forces. Nonpolar leading to London dispersion. That London dispersion, being a weak force, satisfies the conditions that we walked through initially. So B is looking like a pretty good answer. Let's take a look at A, nonpolar covalent, polar covalent. Right away I can stop that analysis. This is going to be a dipole-dipole, okay, which means I can get rid of it. And B ends up being my answer now because it has the weakest force. So this relatively quick interpretation of what those statements mean. What do the words on the page mean? Lots of gas above a liquid. Okay? That then means weak intermolecular forces. That then means strong bonds. You now have to be able to look at those answer choices to identify the bonds types so that you can identify the force types. And that allows you to make these conclusions about physical properties, which is pretty freaking cool. Okay? Which is now going to transition to our last major category, looking at solubility and miscibility. Solubility is the class of anything dissolving in a liquid. Anything. Miscibility is the ability for a liquid to dissolve in a liquid. So miscibility, if we look at this, is a small category within solubility. Okay, which I think are Venn diagrams. Okay, the big thing that we would use for this is primarily realize that when we're looking at this section, we're talking about nonpolar covalent compounds. The rules for ionic compounds, which is kind of asked later in the slide here, the rules for ionic compounds go back to our solubility rules. So you would need to use your solubility rules, that's referencing our double replacement reactions, okay, to dictate how our ionic compounds dissolve in water. What you're using here are how our non-polar covalent compounds interact with water. And the rule of thumb that comes out of that is typically the statement of like dissolves like, which I find a horrible statement because it's too vague. Really what we're talking about is like forces dissolve like forces, which means, yet again, you have to be able to look at two things and you have to be able to very quickly evaluate what kind of forces come out of it. Water is a polar covalent compound. That polar covalent compound leads to dipole-dipole forces. Because I have hydrogen bonded to oxygen, nitrogen, or fluorine, I have hydrogen bonding. When I go through and look at the next one, CH3, that is a non-polar covalent bond, which leads to London dispersion forces. Those would be very different than hydrogen bonding. If we look at our curve, hydrogen bonding's up here, London dispersion's down here. There's a large gap between those, which means they shouldn't interact, or they should not mix. They don't have that like dissolves like aspect. As we continue through that compound, we have another CH3, which is going to be another nonpolar covalent, and then we get up to this OH, which is now a polar covalent bond, which leads to a dipole-dipole force. Because we have a hydrogen bonded to oxygen, we now have hydrogen bonding. And sure enough, these forces are similar. Okay? So if you were worried about trying to kill, say, the coronavirus, you might be mixing ethanol, CH3, CH2, OH, and maybe a little bit of water, and trying to wash your hands off with that. Remember, the percentage of your alcohol has to be 60% alcohol in that water. Okay? So if you're anything under that, you're probably best suited to just drink it and drown away the sorrows. Okay, don't do that because you need to be focused and studying chemistry. When we move to the other system, so this first one, these would mix, these would be soluble. Okay, when we move to the next one, we'd go through and do the same analysis. Water we just went through and did got us to hydrogen bonding. If we go through and look at that other compound, nonpolar covalent, London dispersion force, what happens when we look at the next one and the next one? Still nonpolar covalent, London dispersion. London dispersion and hydrogen bonding are different. These would be insoluble. They do not mix. Okay, so all we're really trying to do is to compare the forces between those compounds. If the forces are the same, we call them soluble. If the forces are different, we call them insoluble. These are a prediction based off of some relatively simple observations. And we're picking the strongest force in each of these cases for those individual compounds and how we would evaluate and process them. Okay? It's shown as an actual multiple choice. Apply the like dissolves like rule. Notice again, this is not a question written by me because I would say like forces dissolve like forces. Rule to predict which of the following liquids is miscible with water. So when we go through and look at this, we see miscible, okay, which is really just them trying to confuse you. This is the same thing as soluble. Okay, we're talking about them actually mixing. So this is same forces. Okay, so that's what we need to find. Which answer has the same force? Therein lies a problem. These are same forces between two things. Okay, our answer choice is very clearly one of those things. What is the other thing? Where's the other structure? This is where we have to read the question carefully. The other structure, they didn't give us as a structure. They wrote it as a name. That would be H2O. H2O is going to give us hydrogen bonding as a force, as we've seen in the other cases. So what we would now go through and do is look at each of these formulas and trying to decide what would be the strongest force. You'll notice in these compounds, they're only giving you formulas, not the full-on structural formulas, so the individual connections between it, which is ultimately a way to simplify this. If we only have carbons and hydrogens, by definition, that's going to be nonpolar covalent and London dispersion force. That is not similar to hydrogen bonding, which means probably not A. Look at B, look at E. All three of those have the same kind of parallels, which means they would be very difficult to differentiate from each other, so we should eliminate those from our answer choices. When we go through and look at C and D, C brings in this chlorine, okay? So we're now looking at a connection between carbon and chlorine. That would be a polar covalent bond, which would lead to a dipole-dipole force. No hydrogen bonding, though, because we don't have hydrogen bonded to oxygen, nitrogen, or fluorine. Dipole-dipole isn't super similar to hydrogen bonding, but if I was given the choice between A, B, C, and E, C is the best answer. Okay, does that make sense? So no, we changed the question, the answer choices. A, B, C, and E. Okay, C is the best option to dissolve because it is the closest in intermolecular forces. Okay, but what does D give us? When we go through and look at D, we should hopefully see that we have the CHs, which is going to again be nonpolar covalent, London dispersion forces, but we should also notice that we see this OH floating out there. That OH is going to be polar covalent, which is going to lead us to dipole-dipole. Do we have hydrogen bonded to oxygen? Indeed we do, and we have hydrogen bonding. What force is the most similar to water's hydrogen bonding? Hydrogen bonding or dipole-dipole? Well, hydrogen bonding, glycerin is the best of these choices to be miscible with water. And what we've done is evaluate solubility based off of those intermolecular forces. And with that, we've actually finished our intermolecular force lecture. So thanks for listening, and sorry it was so long.